Hello, this is a math interest group of NUS High, presented to you the detailed solutions and explanations of past year SMO questions. These questions are from 2018 senior section and I'll be presenting on questions 20 to 25. It is highly recommended for you to pause the video to try out the questions for yourself before proceeding. So this is question 20. 11 identical boxes are arranged in a row. In how many ways can 8 identical balls be put into the boxes if each box can hold at most one ball and no 3 empty boxes can appear consecutively next to each other? Please pause the video right now if you want to attempt this question for yourself. So how do you go about this? I like to first find things that make the question easier. Notice that there will always be exactly 3 empty boxes. Hence, we can treat the scenario that 3 empty boxes are next to each other as one term A, with no other box empty. So this circle part here is A. There are 8 full boxes, has 9 spaces to insert this A among them. The total possible number of cases is 11. Choose 8 is 165 ways. Therefore, the answer is 165. Question 21. Find the minimum positive integer and such that among any n distinct positive integers, there always exist 2 distinct positive integers such that either their sum or their difference is mod of 2018. Again, please pause the video right now if you want to try the question for yourself. So this is a pigeonhole principle problem. Let n be the maximum number that no 2 distinct numbers sum or difference to a multiple of 2018. And by pigeonhole principle, the answer is thus n plus 1. So how do we find this n? So without loss of generality, we start from 1 and we notice that the set 1, 2, 3 all the way to 2009, the set with increments of 1 does not contain any 2 distinct integers that sum or difference to a model of 2018. However, any one more number will result in a sum or a difference that is a model of 2018, but there is one exception to that. Notice that even 0 is not allowed since only positive integers are allowed. The numbers that congruent to 0 mod 2018 are, hence including 2018 brings the total count to 1010 numbers, while still fulfilling the condition. Therefore, the answer is 1010 numbers. Next question, suppose f of x is defined for all positive numbers x, and this term is equal to this term. So find f of 99. So you notice that x minus 1 over x equals to minus 1 over x minus x in brackets. Also notice that 3 times x plus 1 over x squared is the same when you sub in x and 1 over x into the x. So you try substituting 99 and 1 over 99 to see what happens. So if x equals to 99, this expression here equals to the right hand side of this expression here. And if you sub in 1 over 99, the right hand side expression is the same. And therefore, equation 1 left hand side equals to equation 2 left hand side. Then you can conclude that fa equals to f of minus a. So we let x minus 1 over x equals to 99. Hence 2 times f of 99 plus f of minus 99 equals to 3 of f 99 equals to 3 times x plus 1 over x squared. Hence f of 99 equals to x plus 1 over x squared equals to x squared plus 2 plus 1 over x squared. We consider squaring x minus 1 over x, which we get 99 squared. We expand the term, we get x squared minus 2 plus 1 over x squared. Therefore, f to the 99 is x squared minus 2 plus 1 over x squared plus 4 equals to 99 squared plus 4, and therefore the answer is 9805. So question 23. Suppose x, y, and z are positive real numbers satisfying the following system of equations. Root xyz divided by x plus y is 3. Root xyz divided by y plus z is 5 over 2. Root xyz divided by z plus x is 15 over 7. And we find n in this expression here. So please pause the video now. So we consider flipping over the fraction over to get separable terms. That is x plus y over xyz equals to x over root xyz plus y over root xyz, and etc. Then we use multiple addition and multiplication processes between the fractions to hopefully get the answer. To solve this question is that we should flip the three fractions to get x plus y over square root of xyz equals to 1 over 3, y plus z over square root xyz equals to 2 over 5, and z plus x over square root xyz equals to 7 over 15. We take the sum of these three to obtain 2 times x plus y plus z over root xyz equals to 6 over 5, and therefore x over y plus z divided by root xyz equals to 3 over 5. Then we can find the individual parts of this fraction like so. Z over square root of xyz equals to x plus y plus z over square root xyz minus x plus y over square root xyz. And we get 3 over 5 minus 1 over 3, which is 4 over 15. And we can repeat the same process for y over square root xyz and x over square root xyz. Then we flip the three fractions obtained in the last step like so. So square root xyz over x equals to 5, square root xyz over y equals to 15 over 2, and square root xyz over z equals to 15 over 4. And we can obtain these two equations from these three terms. So square root of xyz times 1 over x plus 1 over y plus 1 over z equals to 5 plus 15 over 2 plus 15 over 4 equals to 65 over 4. That's equation 1. And also equation 2, we have xyz times to the power of 3 over 2 divided by xyz, which is simply square root of xyz, which is 5 times 15 over 2 times 15 over 4, which is 1125 over 8. That's equation 2. Then we divide equation 1 by equation 2. We get 1 over x plus 1 over y plus 1 over z equals to 65 over 4 divided by 1125 over 8. So we get n over 900 equals to 130 over 1125. And then we find n using cross multiplication. You should get n equals to 104, and therefore answer is 104. So next question, question 34. In the figure below, the lines AB and C are parallel to each other, and the point F is the midpoint of the line AC, and AP equals to 3AG. And if the area of triangle ABC is 666 cm squared, find the area of triangle CDE in cm squared. So as usual, please pause the video for a while before resuming it. How do we do this problem? There's like a bunch of triangles, a bunch of smaller triangles in one big triangle, and there may be some congruent and similar triangles that we can take advantage of. A lot of ratios are given, so it may be helpful to divide some triangles into smaller triangles. So first of all, let this notation denote the area of triangle XYZ for simplicity purposes, and it is given that area of triangle ABC equals to 666. We draw a line from G to C to divide the triangle, and we can find that triangle AGC equals to 232, triangle BGC equals to 424, since BG equals to 2AG. And since AF equals to CF, triangle AGF equals to triangle CGF equals to 111. So we consider triangles AGF and CEF now. So angle GAC is equal to angle ECA since AG is parallel to EC, and angle GFA equals to angle EFC since there are two straight lines intersecting. And also it is given that AF equals to FC. So by ASA, AGF is congruent to CEF, and hence the area of CEF equals to the area of GF equals to 111. And notice that VG is parallel to CE and D is a common angle, so triangle BGD is similar to triangle CED. So using the similar triangles, we get GE over ED equals to VC over CD. 232 over area of CD equals to 424 over 232 plus area of CD. So we cross multiply and we get area of CD equals to 232. Now the final question, question 35. For any real number x, let this notation, I'm call it the floor function, denote the largest integer smaller than or equal to x. For example, floor 3 equals to 3, floor 2.8 equals to 2, and floor negative 2.3 equals to negative 3. And suppose that r is a real number such that this left-hand side term equals to 2018, and we find floor of 20r. So, since we're dealing with floor functions, we can begin by estimating any number r such that 99r is close to 2018. So firstly, we find the integers that r lies between, then we find specifically between which fraction of 200 that r is in. So we let the left-hand side approximation be denoted by a, and the approximate value of r is 20, and therefore 20 times 99 equals to 1980. And when I equals to 21, this whole left-hand side term a equals to 20 times 99, since every time is reduced by 1 equals to 1980. And when I equals to 22, a equals to 2079. And as r is between 21 and 22. Now we find how many times an a gets reduced to 20 by the floor function and how many gets reduced to 21. So 2079 minus 2018 is 61. Hence 61 times an a when floor is reduced to 20, and 38 times is reduced to 21 from 21 point something. So a equals to 38 times floor r plus 61 times floor r minus 1 equals to 38 times 21 plus 61 times 20 equals to 2018. and therefore R is between 21 and 38 over 200 and 21 and 39 over 200. And you multiply all terms of this inequality by 20, we get 420 and 38 over 10 is smaller than equal to 20R is smaller than 420 and 39 over 10. We convert the two upper and lower limits into decimal and we get R is between 4 to 3.8 and 4 to 3.9. So floor of 20R is 420. Also my mistake here, it's 20R here, not R. So answer is 423. So this is the end of the video and I hope this helped you for SMO. And some of the general tips is that you shouldn't spend too much of your time on one question and you should like plan your time carefully and skip difficult questions. I remember the time I spent 20 minutes on one question in SMO, and so don't be like me. And also if you're like interested, please consider joining MIG. Also like this video, subscribe to our channel, and I wish you the best of luck for SMO.